recording. All right. Last class ended our preliminary discussion on reactions. Over the last 3 classes, we've covered a lot of content. More than anything, one of the biggest points of the last couple of chapters, last couple of lectures, is starting to understand the cumulative nature of this course. At the very beginning of the semester, I described a little bit about how when we think about how chemistry builds on itself, I like to think of it like an English class. During the beginning weeks, you learn the alphabet. Then you learn words. Then you learn sentences, paragraphs, and eventually by the end of the semester, you'd be writing essays. In the same way, reactions builds on itself. As you can see over here on the top, the little outline, when we went over reactions, we covered three big subtopics. Number one was balancing chemical reactions. That was what we went through piece by piece, ion by ion to balance it on both sides. We also talked a little bit about state symbols and solubility rules. In state symbols, we introduced the concept of an aqueous state symbol. And the term aqueous quite literally refers to the fact that some chemicals are dissolvable in water. Why water specifically? Because most reactions take place in water. Heck, for all of the reactions you will see in 1A and 1B's lab, they will almost all be in water. To identify if something is a solid or aqueous, you simply refer to the solubility rules table. Again, I will remind you that you will be given this table as part of your exam booklet, so you don't need to memorize it, but you do need to know how to use it. Once we covered solubility rules, we then went over the various archetypes of reactions. Number one was combustion. These are hydrocarbons that react with oxygen and will always form carbon dioxide and water. We then went over the generic idea of synthesis, which is 2 or more chemicals combining together into one. Our discussion on synthesis led to a brief foray into decomposition, which is just the exact opposite of synthesis. In other words, whereas synthesis combines two chemicals together, decomposition breaks the compound into its individual chemicals. That then led us to our discussion of the displacement reactions, both double and single displacement, where in double displacement, those chemical compounds swap partners. The generic reaction shown was AB plus CD to give you AD plus CB. In stark contrast, in single displacement, whereas instead of chemical compounds swapping partners, in single displacement, one element replaces another. Generically shown here as A plus BC, giving us AC plus B. Now, the very nature of single displacement suggests that that single element will replace another. In other words, this single element can either replace the cation B, or it can replace the anionic C. How do we know which one it will replace? Well, it just simply depends on the chemical that we have at hand. For example, sodium is a cation, it's in group 1, so it will most likely replace the cationic lithium. Chlorine from group 17 will have a -1 charge and will replace the anionic fluorine. From there, we really started our big discussion on what type of questions we could expect, which really come back down to this question right here. Provide a complete balanced equation for the reactions below, including state symbols. I even went so far as to say that each question would be worth approximately 3 points, where 1 point is for the correct products, 1 point for correct balancing, and 1 point for the correct state symbols. We went through the process of predicting the reaction. Number 1 is identify the archetype. Then we will match ions and crisscross as needed. And finally, we will balance and include state symbols. I want to reiterate what I said last week. The order, the procedure is meant to be followed in order. More often than not, when I see students are making mistakes, it's because they've skipped from 1 to 3, completely ignoring number 2. I understand wanting to balance stuff out as soon as possible, but it's one of the last things that we do, as well as state symbols. We then covered various subcategories of reactions. These are not necessarily archetypes that are used to predict reactions, but these can be called as classifications based on a reaction. For example, gas evolution. As the term suggests, in gas evolution, a gas is formed. This is not something you could necessarily predict, but it's a classification you could assign after the fact. In other words, looking here at the reaction between iron and HCl, we result in FeCl and H2. H2 is a gas. It's one of those diatomic elements. That's how we know this is a gas evolution. That then led us to our discussion of the curious case of H2CO3. H2CO3 has a unique ability that whenever it is formed, it will always decompose into H2O and CO2. So recognizing that this is formed is something you do have to pay attention to, and then recognize that the final answer is not one with H2CO3, but instead with the broken down H2O and CO2. We then cover the basic idea of a neutralization and precipitation reaction. In neutralization, water and an ionic compound is formed. An ionic compound is a metal and nonmetal. We then went over precipitation, in which a solid precipitate is formed from non-solid reactants. The last two wet labs that we did, identifying unknowns, observing chemical reactions and going through that flow chart to identify unknowns, taught us a lot about what these reactions look like in the real world. We then talked a lot about redox, reduction oxidation. We spent a lot of time on this particular topic because not only does redox involve the direct transfer of electrons, we do need to understand the principles of oxidation and reduction. I won't go over this again in detail because we went into this in length. But most recently, on Monday's class, we covered the concept of an ionic equation. An ionic equation is not a new reaction, nor is it a new reaction archetype. It is simply a different way to write reactions focused on chemical changes. The steps are simple. We'll write the fully balanced equation first. Then we'll write the complete ionic by breaking apart all aqueous species. Then we will identify and remove spectators. These are the ions that do not change. And then finally, we will write the net ionic equation. What just happened? This is like the second time this has happened in the last couple of weeks. Last time I just needed to turn it on. Yeah, okay. I guess the TV has a timer. And that's pretty much where we ended our discussion of reactions. Today, we're going back to our mathematical roots, and we're introducing a new concept titled stoichiometry. Stoichiometry is also referred to as mole ratio. Now, to understand the concept of stoichiometry, we're actually going to go a little bit really basic. We're going to actually go into the kitchen. We're going to make a sandwich. To make a sandwich, we traditionally need 2 slices of bread. Let's say 1 slice of cheese. And for the sense of this argument, let's do 2 slices of our meat. And that, of course, gives us 1 sandwich, written here as SW. Now, throughout the semester, I have frequently described chemistry as well as its reactions, very similar to something like cooking or baking. The idea that you'll be mixing things together, allowing them to cook, ferment, bake, or whatever. But more importantly, that there are general ratios expected of you. You see, the point behind these ratios is, of course, we know how many of each ingredient we need. For example, we need 2 slices of bread to make 1 sandwich. We need 1 slice of cheese to make 1 sandwich. And we need 2 slices of meat to make 1 sandwich. But the beauty of these ratios is that it allows us to make predictions. If you've ever tried to look up a recipe online, you probably have read something along the lines of, the following recipe will feed 4 to 6 people, adjust based on how many people are eating. And that's exactly what we do with stoichiometry. Whereas in another way, if, for example, we had 4 slices of bread, we would make in total 2 sandwiches. That makes sense. If 2 slices of bread give us 1 sandwich, then 4 slices of bread will give us 2 sandwiches. But the thing about ratios, the thing about cooking, the thing about reactions, is that it's not a one and done game. Everything is affected. To make 2 sandwiches, we specifically need 2 slices of cheese. To make 2 sandwiches, we will specifically need 4 slices of meat. So the idea here is that although the reaction explicitly tells us the ratio, those ratios can be used to make predictions about other ingredients or the product. Let's say, for example, you had friends come over and your friends were like, hey, can I get a sandwich? Do you mind making that for me? And you say, okay, fine. You go into your pantry and you recognize, oh, I see I have 10 slices of meat in total. Well, you know, just based off of the meat, that the most amount of sandwiches you can make would be 5. Reactions work in the very similar fashion. We can use information we know about one item to determine information about another item. This is the very basic idea behind stoichiometry. It is using the ratios that we see and know to make predictions. Now, going back to our calculations a few weeks ago, right before we did reactions, we covered what was known as the mole concept. We covered the idea that the molar mass of anything is equal to 1 mole of that anything, which is simultaneously equal to 6.023 times 10 to the 23 atoms or molecules, depending on the chemical you're referring to. We, of course, understand in principle how to calculate the molar mass of a chemical compound. That's just adding up all of the masses. We understand what a mole means. If you recall, this was a chemical currency. And 6.023 is Avogadro's number. The 2 formulae that we had developed back then was number 1, N is equal to M over MM. And N is equal to capital N. Oops, made that. Capital N over N sub A. Reminding ourselves what these individual variables refer to. N stands for moles. Lowercase m refers to the mass of the sample. MM refers to molar mass. In the other equation, same idea. N is moles. N is the number of particles. This can either be atoms or molecules, just depending on what chemical we're referring to. And Na is Avogadro's number, that constant 6.023 times 10 to the 23. Based on this, if we assume, for example, we have chemical A, generic chemical A. Using the equations and expressions we just saw up here, we can quickly relate the mass of chemical A to the moles of chemical A. And the link between these two is the molar mass. As you might remember, we just talked about this. N is equal to M over MM. And just so we're absolutely clear, I'll put the abbreviations beside them. Mass is lowercase m, moles is M. We can actually make a similar diagram for another chemical. Let's call it chemical chemical X. The exact same chart, mass and moles are related to one another. But the concept of stoichiometry allows us to link these two charts together. that blue arrow right there. You see, previously, what we are able to do is individually calculate mass and moles of a single element or chemical. Similarly, we can calculate it individually. But now we're introducing the idea that we can connect the two through stoichiometry, aka mole ratio. I have drawn this diagram on the board. That way we can continually refer to it, so I don't need to keep scrolling back and forth. But take a second to draw this map. All right, let me just move on to the next page. I'll repaste it, don't worry, it'll still be present. This map allows us to make very easy and simple assumptions about the math required of us, because in a lot of ways, I'm calling it a roadmap on purpose. It's what allows us to figure out the direction to solve, what to solve, and what to solve it with. I know right now that seems very subjective, very vague a statement. So let's actually try a question. So the reaction is between aluminum and HCl, which reacts to form AlCl3 and H2. First question asks, how many moles of aluminum are needed to produce 0.334 moles of AlCl3? One of the first things I want us to note is that the given equation, as written, is unbalanced. I have given you, of course, the correct products. I have given you the correct state symbols. But as of right now, it is not balanced. And as we just talked about with the sandwich analogy, we kind of need to know what the ratios are to invoke stoichiometry. But before we get there, let's just take a second to understand what we've been asked for and what we need to do. I'm going to replace the generic chemical A and chemical X with the chemicals in question. The question literally says, how many moles of aluminum? Okay, so we know based on the question, what we're ultimately trying to find is aluminum, are needed to produce 0.334 moles of aluminum chloride. There's that second chemical mentioned, AlCl3. It does not matter the order which you place this in. Something I want us to understand very clearly is that all of this right here is really just scratch work. It allows us to organize our thoughts. Now what we're going to do is we're going to fill in the chart with the information we know and the information we need to find. We know that we're dealing with 0.334 moles of aluminum chloride. 0.334. Notice I put it in the appropriate box, specifically talking about aluminum chloride, and we've been given the number of moles. The question asks us how many moles of aluminum are needed. So ultimately, what we're trying to find is the moles of aluminum. So to make that simple, we just put a question mark in the box. By putting these values in the box, we can clearly see the path ahead. In other words, for us to understand how many moles of aluminum we need, we start here, we end here. So the only thing we need to do is use stoichiometry to figure out the answer. Stoichiometry, of course, is mole ratio. So we do need to take a second to balance the equation. 1 aluminum, 1 aluminum. 1 hydrogen, 2 hydrogens. No big deal. We'll just put a 2 in front of the HCl. Aluminum is balanced. Hydrogen is balanced. 2 chlorines, 3 chlorines. That's a bit awkward. We're going to look for the lowest common multiple. We're looking for 2 and 3, so we're going to multiply AlCl3 by 2. In doing so, we get in total 6 chlorines. To balance that, we'll just put a 6 in front of the HCl. So now the chlorines are balanced. In my attempt to balance it, I've actually messed up the hydrogens. Now there's 6 on the left, 2 on the right. Quick fix though, just put a 3 on the right. And of course, I've also messed up the aluminum. There's 2 aluminums on the right, 1 on the left. To fix that, we'll just put a 2 on the left. Now the reaction is balanced. We had to put in the effort to figure it out. Now we can clearly see the ratio between aluminum and aluminum chloride is 2 to 2. Where do those numbers come from? They're the balanced numbers in front of the chemicals. For every 2 aluminum, we form 2 aluminum chloride. This 2 to 2 ratio can actually be further simplified. A 2 to 2 ratio is equivalent to a 1 to 1 ratio. What this means is that for every 1 mole of aluminum chloride, we need 1 mole of aluminum. If we need 2 moles of aluminum chloride, we'll use 2 moles of aluminum. If we need 3 moles of aluminum chloride, we'll need 3 moles of aluminum. We need 0.334 moles of aluminum chloride based on the 1 to 1 ratio. We know that we'll be using 0.334 moles of aluminum. And that right there is our final answer. .334 moles. And remember, the reason why we were able to make this so easy is because this was a 1 to 1 ratio. So this is the simplest case. You plug in the values, they're right beside one another, and the ratio just happens to be 1 to 1. That's the simplest case. You don't need much math. You don't need your calculator. You just need to recognize what you're working with. But let's do a follow-up question. How many grams of HCl are needed to react with 0.545 moles of aluminum? All right, listen to what the question is saying. It's asking you one question about one chemical. It's asking you something about HCl. And it's given you information about another chemical. The structure of this question is what tells us we'll be using the roadmap. So we're going to get it at the ready. The chemicals we are dealing with in this question: number 1, HCl. Number 2, aluminum. It does not matter left or right, which one, wherever it is, because they're both saying the same thing. The question outright asks us how many grams of HCl are needed. So we know based off that wording, that's what we're trying to find. So we're going to put the question mark. We know based on the question, we're told that we're dealing with 0.545 moles of aluminum. So we write that number in the appropriate box. The path ahead should be clear. We're going to start from the 0.545, use mole ratio to get moles, then use the molar mass to get the mass. And herein lies the power of the roadmap. You see, the reason why students struggle with this topic so much is because it's a lot to keep track of in your head. Even with use of formulae and numbers, it's very hard to understand, what do I do first? What do I do second? What do I do third? The roadmap takes care of that ambiguity for you. By simply filling in the relevant boxes, we're able to see and say very clearly, the first thing we're going to do is use stoichiometry to get moles. The second thing we're going to do is use molar mass to get mass. Of course, as of right now, there are a few details missing. Number one, we do need to know the molar mass of HCl. Number two, we do need to know the stoichiometry of the two reagents. Now, I like to describe this as a roadmap on purpose. I like to think of this as a starting point and an ending destination. I also like to think of these arrows in the middle as a bus pass, meaning you're going to go from one destination to another using that bus pass. You're going to go to that final destination using that bus pass. So right now, what we're going to do before we start any real serious calculations, we're going to first identify the mole ratio. Then we're going to quickly calculate the molar mass. Starting with the stoichiometry, remember, we've already balanced the equation. That was something we did from the very beginning. So we've already balanced it. We're focused here on HCl and aluminum. We see here that the ratio is 6:2. So I'm going to write that in. 6:2. Now, I want to be absolutely clear on something. From the balance equation is where we got the numbers 6 and 2. However, if you had written 2:6, this would be incorrect. Why? Because the way how you're writing it implies that there are 2 HCl's and 2 and 6 aluminums. That is not correct. So the order that you write the ratio does matter. The order that you write these guys up here, it doesn't matter at all. In fact, if I had left the left side as Al and the right side as HCl, this would be 2:6, because that's the order I wrote it in. We have the stoichiometry. All that's left is the molar mass. To get the molar mass of HCl, we simply add the molar masses of hydrogen and chlorine. In total, this is approximately 37.5 grams. So we'll write that number in, 37.5 grams. With that, we have everything we need. We know our starting point. We have our bus pass. We know where we're going to stop over or layover. We have our bus pass for the final destination. We know to get right there. Recognize up till this moment, we have not at all discussed or mentioned or even spoken about the mass of the aluminum. The simple reason is it's not needed. It wasn't given to us in the question, and the path ahead does actually not need the mass of aluminum at all. So just to make it easier on us visually, I'm going to erase that side of the roadmap, just to make it easier on us visually. I see a hand, Sarah. Sure. There is no reason to believe in this question that you're dealing with isotopes. I would have to specify that for you. Yeah. Otherwise, if not specified, you are allowed to assume that it's from the periodic table. So that's where we get the masses from. Did I make a math? Oh, right. Chlorine is 35.5. I see. That's maybe, is that where I made the mistake, Sarah? Is that what you were asking about? Okay, no, that's, okay, so that's a different thing. I made a mistake. The mass according to the periodic table for chlorine is 35.5 added to the 1 for hydrogen. This should actually be 36. I apologize for that. All right. Now that I have this whole thing set up, I'm going to need more space, so I'll go to the next page. Like I said, the path ahead now remains clear. The first thing we're going to do is we're going to use mole ratio. Then the second thing we're going to do is use the molar mass. I like to label my calculations. That way, when I review it, I know exactly what I'm doing. So I'm going to write here, number 1, mole ratio between HCl to aluminum. I like making these kind of notes when I do my math. So that way, when I review it, I know exactly what my thought was, instead of trying to remember. Now, unlike mass mole calculations, there is no explicit formula to do mole ratio. You do have to put in a little bit of effort to figure it out. And here's how the setup looks. We are going to compare hydrogen chloride to aluminum. And we know that the mole ratio is 6:2. What we don't know, or unknown, is how many moles of HCl are there for 0.545 moles of aluminum. So let me go over that once again. This is basically a matrix, a 3x3 matrix. Like so, but just with colons in the middle. We know the stoichiometry because we spent time balancing the reaction. So that's what we know. We know the stoichiometry. What we don't know, the unknown, is if we're using 0.545 moles of aluminum, how many moles of HCl will be needed? As of right now, this is unknown. Hence the setup X to 0.545 and then 6:2. Those of us who may be math inclined may already know what I'm about to do next. Now we are going to cross multiply. By cross multiplying, what we get is 2 times X, 2X, equal to 6 times 0.545. Ultimately, we're trying to solve for X. So to get X alone, we're going to divide both sides by 2. This is what gives us a very easy expression to calculate X, 6 times 0.545 divided by 2. Hopefully we brought our calculators. Let's take a second to do it. I have the calculator up on the screen. Let's plug it in. On top, we have 6 times 0.545. On the bottom, we have 2. That leads us to our answer of 1.635. I see your hand, Joel. I'll get to you in a second. That's, of course, what tells us the number of moles of aluminum of HCl is 1.635. Now, 2 things I'd like to point out. Just as we saw earlier in the case of 2:2, we simplify this to 1:1. You could have done the same thing here for 6:2, making it 3:1. If you had done that, you would still eventually get the same answer. So the point to take away from that is simplifying is easier, but it's not absolutely needed. The second thing I'd like to point out is the significant figures and decimal places. Remember that it's on me to incorporate in the instructions something about significant figures or decimal places. I need to say in the question, report your answer to the appropriate significant figures. Report your answer to 3 significant figures. If I don't say that in the instructions anywhere, that means I'm not grading for it. And in cases where that happens, by default, with no instructions, 2 decimal places is sufficient. So this one becomes x is approximately 1.64. All right, Joel, did I happen to answer one of your questions? Or okay, great. Okay, we've taken our first bus and we've gotten to the moles stop. All that's left is to go from moles to mass. So number 2 is to go from moles to mass. You see, the beauty of the roadmap is everything is already there for you. You have just filled in the moles, check. We've already calculated the molar mass, check. And all we need to solve is M. So bringing that formula back, N is equal to M over MM. With a little bit of manipulation, we're able to get M is equal to N times MM, where we know that N is 1.64. We just calculated that. And the molar mass is approximately 36.5 grams. We calculated the molar mass. It was one of the first things we calculated, the molar mass. Once we have that, we can then plug into our calculator 1.64 times 36.5 for a whopping total of, what was that number? 59.86. This is mass, so it's in grams. This right here is our final answer. You could redraw it into your chart if you so choose. 59.86. You don't have to. Remember, ultimately, I did say that think of this roadmap as your scratch work. And as you know by now from your first exam, I don't look at your scratch work. I don't collect the scratch work. But this right here is our final answer. Sarah.
Before this question, we did see mass, but it's like the whole table would have had to be filled out. Is the mass aluminum just the same 3-to-1 ratio that we came up for 80 volts?
So when you say the mass of aluminum, so you're saying what if we had been given this value right here? Are you referring to the what's in the box or what's between the arrows? What's in the box? So if we had been given, for example, if the question said instead of 0.545 moles, if it had instead say, what if you were working with 11.3 grams, you would write 11.3 grams in, and you would continue the roadmap as is. You're going to get some practice with this with today's dry lab workshop because it's on this topic. Any other questions on anything we've done so far? Which one? Okay. Yes, Joel.
Well, the number of moles work in the ratio for mass just ratio.
Correct. This goes back to our discussion of currency. We can easily convert currency from USD to JMD to rupees to pounds. The reason why we love the mole is because it can be easily converted to other chemicals. You could not be able to easily do that for masses. That's why it's specifically called mole ratio. Okay. That then leads our discussion into what is known as reaction metrics. Now, we of course understand that there are various things that we can measure about a reaction. You all saw it in lab. You can get mass, you can get volume, you can measure mass, you can get the volume of the product, all that nice stuff. But every once in a while, we do want to measure the success of a reaction. To measure the success of a reaction, we calculate what is known as percent yield. Percent yield is equal to the theoretical yield. Here just is written as Y for yield, divided by the actual yield times 100, because of course it's a percentage. The difference between theoretical and actual is a very simple distinction. The theoretical yield is what you calculate. The actual yield is how much is actually made in the experiments. This is a key distinction. You see, the truth is, as much as we'd want to believe it, not every reaction is 100% successful. There are many factors at play that affect the success of a reaction. Number one being its environmental conditions. Some reactions prefer high temperatures. Some reactions prefer low temperatures. In other cases, it could be human error. Maybe you spilled some of your product in the process. Now your overall amount has decreased. So the key distinction between theoretical and actual is actual yield is a number that is based on how much you actually made in the experiment. This is not a number you would be able to calculate. It's a number I would have to give you. Theoretical yield is something you can calculate. So let's us try a question using the reaction we just did. So let me just grab that reaction back. And solve a question about it. Part C. What is the percent yield if 0.25 moles of hydrogen are, and I'm going to put this very nice and clear, are actually made if 3.33 moles of aluminum are used. So same reaction, a reaction we've already balanced. The question is asking us, what is the theoretical yield? We know from the formula for theoretical yield, percent yield. And we know from the formula for percent yield, we need to know the theoretical yield. We also need to know the actual yield. The question does tell us explicitly what the actual yield was. You can see the word right here. This is where I say it's on me to make it clear to you what the actual yield is. 0.25. Then it says 3.3 moles of aluminum are used. So as of right now, we have the actual yield. We know that's 100. What we need to find is a theoretical yield. We need to know, in theory, how much hydrogen can we make based off of the amount of aluminum that we use. This is what tells us we're going to get that roadmap once again. Give me a second just to erase some stuff. Okay. We are comparing aluminum to hydrogen. And let's see what we've been given in the question, what else we know, and what we don't know. We are told explicitly that we are using 3.3 moles of aluminum. So we plug that in, 3.3. To get the percent yield, we need the theoretical yield. In other words, we need to know, in theory, how much hydrogen will we make based on 3.3 moles of aluminum. The path ahead becomes clear. We're going to go from moles using stoichiometry to moles of hydrogen, and then moles of hydrogen to mass of hydrogen. What are we missing right now based on the chart? We're missing the molar mass of hydrogen. We're also missing the stoichiometry. Let's quickly fill that in. The molar mass of hydrogen is incredibly simple. It's actually just 1 + 1, 2 grams. The stoichiometry, the mole ratio between aluminum and hydrogen, let's go up and see it. Aluminum to hydrogen. Remember, this was already balanced. We spent time on it. It is 2 to 3. So I write that. Is what I've written correct? No. The mistake I made here was I mixed up the numbers. Remember, the order matters. There are 2 aluminums, so the 2 must be on the left. 2 to 3. The path ahead now is clear. We can just erase some stuff just so we can make it a little bit clearer for us. We see, of course, we're going to go from moles to moles, then moles to mass. Very first thing we do is mole ratio. We are comparing aluminum to hydrogen. We know, here abbreviated with a K, that the mole ratio is 2 to 3. We know that. That is the known mole ratio of aluminum to hydrogen based off of the balanced equation. What we don't know is if we have 3.3 moles of aluminum, how many moles of hydrogen will be formed? We've set it up correctly, so all we need to do now is cross multiply. That leads us to 2x is equal to 3 times 3.33. To get x alone, we divide by 2. If we put this into our calculator, 3 times 3.33 divided by 2, that gives us a final answer of 4.995. We plug that in to the chart so we can keep track of it. And we're not done just yet, because we need to know the mass of the hydrogen. So step 2 is going from moles to mass. We know the formula we'll be using is N is equal to M over MM. A little bit of rearrangement. The equation becomes M is equal to N times mm. We know the number of moles is 4.995. We know the molar mass is 2. We can now plug this into our calculator, 4.995 times 2. And this gives us 9.99 grams. You, of course, are able to round this up. When rounded, this becomes almost a perfect 10. And with that, we have calculated, in theory, how many grams of hydrogen we should make. Let's go back to the question. The question said, what is the percent yield? So we're going to go back to our expression right here. We know that percent yield is equal to the theoretical yield, that's Ty, divided by the actual yield, Ay, times 100. We know that the theoretical yield is 10 grams. That's what we just calculated. And we know from the question that the actual yield is 0.25 moles. As written, this should bother you. As written, the fraction should bother you. What should bother you specifically is that the units are not the same. We have to have them be in the same units. They could either both be grams over grams or mole over mole, but they have to be the same. We could convert the 0.25 moles to grams, but we could also remember, hey, didn't we just calculate the number of moles for that 10? Wasn't that something we did on the way? Absolutely. So instead of saying the theoretical yield is 10 grams, we're going to say it's 4.995. We put this into our calculator. 4.995 divided by 0.25 times 100 gives us an almost 2,000% yield. Does this mean you are wrong? No. A percent yield is just a measure of the success of the reaction. Sometimes the percent yield will be less than 100. What this implies is that the reaction is ongoing. In other words, we assume that the reaction is still working because we're not yet at 100% yield. When the percent yield is equal to 100, this is what we consider a complete reaction. When your yield is over 100, that means something went wrong in the experiments. None of these percent values are inherently wrong. They just tell us something about the experiment. So occasionally you might get percentages of almost thousands of percent. It's not that you did anything wrong. Again, it's just a reflection of the equation, of the reaction at hand. Now, in this case right here, based on the question at hand, we were asked about hydrogen and we were given information about aluminum. But occasionally, what if I give you information about both reactants? Let's do a question for that. Here's a new reaction. Carbon added to sulfur. Gives you carbon disulfide. And the question is, determine the theoretical yield of CS2 made when 12 grams of carbon reacts with 32 grams of sulfur. Actually, let me not make that 32. Let's make that 23. 23 grams. Okay. So first and foremost, the number one thing we want to do, we want to check, is the balancing of the reaction. It is every student's responsibility to confirm or question whether or not the given reaction is balanced or not. Of course, it'll be in the instructions, the following reactions are balanced, the following reactions are unbalanced. But no matter what, it's always your responsibility to double check. So to quickly balance this, all we need to do is just put a 2 in front of the sulfur, and that actually just takes care of the balancing. There's 1 carbon on the left, on the right. There's 2 sulfurs on the left, 2 on the right. So here's the challenge now. I'm asking you to give me and find information about 1 chemical, yet I've given you information about 2 other chemicals. In other words, I could foreseeably have 2 roadmaps that connect between carbon and carbon sulfide and sulfur and carbon sulfide. The question is, how do we know which one to use? The simple answer is we don't. We're going to draw 2 roadmaps. Over here, we'll compare carbon and carbon disulfide. On this side, we'll compare sulfur and carbon disulfide. We know what the roadmap roughly looks like. We know what the boxes are. Don't forget it's up there on the board. And remember, ultimately, these roadmaps are your scratch work. So as you come into your own with practice, you'll be able to shorten it or abbreviate it in some cases. For example, I'm just going to write M, N, M, N, M, N, M, N, where M and N represent mass and moles respectively. I know that my vertical arrows are traditionally molar mass. And I know that to connect the 2 chemicals is the ratio. Since we've already balanced the equation, the ratio is something we can very quickly write. The ratio between carbon and carbon disulfide is a very simple 1-to-1. Let me put that in a different color, actually. 1-to-1. We see that the ratio between the sulfur and the carbon disulfide is 2-to-1. So we plug those in immediately. We can also very quickly get the molar masses of all of these compounds or elements. We know that from the periodic table, the molar mass of carbon, just carbon, is 12.01. Need some space. I'll write it over on this side. 12.01 grams. To get the molar mass of carbon disulfide, we'll need carbons plus 2 sulfurs. Carbon is 12.01. Sulfur is approximately 32.07. If we plug this into our calculator, let me just put it on mine very quickly. Put it on my handheld one. 32.07 times 2 plus 12.01. We get 76.15. Filling in the rest of the roadmap on this side, we've just calculated the molar mass of CS2. That's 76.15. And the molar mass of sulfur is approximately 32.07. As of right now, all I have done is build the roadmap. I have not started with any calculations, any analysis. I've just built the roadmap. In both cases, we're being asked to find the theoretical yield of carbon disulfide. So those are our question marks. In the same question, we're told the mass of each element. We're told that for carbon, it's 12 grams. We're told that for sulfur, it's 23 grams. As of this moment, we are done looking at the reaction equation. We are done looking at the question because everything we need to know, everything we need to calculate is right here in the roadmap. In both cases, the path ahead is clear. Mass to moles, mole ratio, moles to mass. Mass to moles, mole ratio, moles to mass. Now we're going to work on one at a time. I'm going to pick the left side first. The very first thing we are going to do is go from mass to moles. M to N. I know that traditionally N is equal to M over MM. This is what tells me the mass 12 divided by the molar mass 12.01. This will be approximately equal to 0.999, which we can round up to a flat 1. I always like to actually keep track of my numbers by incorporating them into the roadmap. That way I understand what's going on. Now we have a very simple math section. The ratio is 1 to 1. I don't need to put in much effort for the math or the calculations there. If the ratio is 1 to 1, then we need 1 mole of CS2. Again, there was no math or calculus required in this step because the ratio is a simple 1 to 1. The last step, of course, is going from moles to mass. So just the second step, I'm going to write 1 to 1. That way I can understand when I review my notes that I didn't need to do a calculation. Number 3, we're going from moles to mass. We know we'll be using the formula M is equal to N times MM. We've seen this enough times by now. We know the number of moles is 1. And we know the molar mass is 76.15. 1, any number times itself is itself. That's how we know that the theoretical yield of CS2, according to carbon, is 76.15 grams. Now we're going to do the exact same thing, but on the right-hand side with the sulfur. First things first, we're going to go from mass to moles. Number of moles is equal to the mass over the molar mass. That is 23 divided by 32.07. Putting this into my calculator, I get 0.717. I can approximately round this to 0.72. Now we're back at the ratio step, mole ratio right here. Now, those of us who are more math inclined, you're probably able to do this step in your head. If you recognize that this is 2 to 1, if this is 4, this is 2. If this is 6, this is 3. If this is 10, this is 5. So in other words, some of us math inclined may be able to understand we're just dividing it by 2. But I will always recommend you put in the effort. Step 2, we are comparing sulfur to carbon disulfide. We know the ratio is 2 to 1. What we don't know is if we're dealing with 0.72 moles of sulfur, how many moles of carbon disulfide will we have? We cross multiply, we get 2x is equal to 0.72 times 1. Anything times 1 is itself. Dividing both sides by 2, we get x is equal to 0.36. We can now put this into our flow chart. That way we can just keep track of things. And we can clearly see the next step is from moles to mass. Moles to mass. Using the formula, mass is equal to moles times molar mass. We just calculated the moles as 0.36, and we previously calculated the molar mass as 76.15. Putting this into my calculator, I get approximately 27.31 grams. So two big roadmaps that lead us to two completely different answers. Based on carbon, looking at the roadmap, we can theoretically form 76 grams. Based on sulfur, we can theoretically form 27.31 grams. How do we know which one to choose? Here's where I'm going to put it right here. The lesser amount is the theoretical yield. The lesser mass is the theoretical yield. Because in other words, what we are claiming is that that is the minimum amount we predict we can make. This is the big, big takeaway right here. The lesser amount is the theoretical yield. Elena, what's your question?
Questions on exams, would you specify if you want us to put the answer in grams, or would you be able to answer with just the 0.6 moles?
I can tell you that your exam for these questions are going to be multiple choice. So it just depends on what the options are given in the question. But I can tell you right now, this type of question is going to be multiple choice. Yeah. This is what now tells us that our theoretical yield is at 27.31. We're still not done with the question. Wait, no, wait, yes, we are. We're now done with the question. It's asking us to determine a theoretical yield. So the final answer is 27.31. The last topic we'll cover for today is what's known as the limiting reagents. Sometimes you might see online or in textbooks limiting reactant. In principle, the limiting reactant is what bottlenecks the reaction. The reason why we call it bottlenecks is because once the limiting reactant is used up, meaning once it's finished, the reaction stops. The limiting reactant is the reactant that leads to the theoretical yield of products. And as we just talked about on the other page, the theoretical yield is the lesser amount of product, formed. So in the question we just did, where we were asked to find the theoretical yield of carbon disulfide based on two reactants, ultimately what we found out was that the theoretical yield is 27.31. That's the lesser amount. The reactant that leads to that lesser amount is known as the limiting reactant. So in the previous question, sulfur is the limiting reactant. In general, there is only one limiting reactant per reaction. This is true, like I'd probably say like 99% of the time. Very rarely is it possible for multiple things to be the limiting reactant. What this means is that all other reactants are in excess. Where the term in excess just means that there is just so much of it, which is a pretty neat term to just contrast against limiting reactants. So I could potentially ask you in the question, determine the theoretical yield of carbon disulfide. Part B, what is the limiting reactant in the question? And of course, to that you'd simply say the sulfur. Do we have any questions? Yes, Joel. I don't have one off the top of my head. When I look at today's workshop, I'll just go through my answers and I'll see if that's one that we can do together. Yeah. Today was a lot. We've built upon our basic fundamentals of reactions and now we've introduced chemical calculations. In today's workshop, let me just bring up the schedule so you can see it. Today's workshop is focused on reactions and stoichiometry, so we'll get some more practice. And then Monday's lecture is designated as an open practice day. I know it's labeled as reaction metrics, but clearly we were able to get to it today. Because Wednesday, of course, is your module exam. What this means for Monday's lecture, it'll be more or less like office hours type open review for the exam. No new content will be taught on Monday. I still expect you to show up because we still have an experiment that day and the following Wednesday is your exam. But as of right now, that is the end of module exam 2 contents. I kind of already gave it away when I answered Elena's question about how the exam is going to be structured. But come Monday, I'll give her a much more firmer answer because I've already made the exam by then. I kind of already gave it away, though. I said that a lot of these calculation-based questions will be multiple choice, but I'll give you a confirmed answer on Monday. It is 1:15. We're going to end lecture for today. We do have a workshop in 15 minutes. Go ahead and take a break. I'll see you guys in about 15 minutes.